Subunit 3.8, Phase F. Okay, let's talk a little bit about Phase F, the closeout phase. This is the last part of the life cycle. This is the last phase. And the end of a system's life is just as important as any other phase. And so there is a lot of activity that happens even here at the end. One goal of this period is to assure that any of the science data and engineering data that have been returned by the spacecraft throughout its life cycle have all been archived in a way that they can be easily accessed by the scientific community or the engineering community to be able to do further studies, right? So you've been collecting all this science data throughout your mission life. There might be much more data than could have been analyzed during the time the satellite was actively operating. And so you want to make sure that all that data is available so scientists for many years after that can continue to look at that data, analyze it, and be able to form new conclusions and do more analysis on all that data. So similarly, you've been bringing back engineering data throughout the life of the satellite's operational phase. And so all of that engineering data on the health of the subsystems or how the components operated during maneuvers when you were firing thrusters or during the periods when you were going through eclipse and batteries were providing energy. So all of that data on how the system performed is also important because other satellite designers might want to come in and look at it. They might be thinking of a similar design for their power system or propulsion system. And they might want to assess, well, gee, how did yours operate when you actually put it on orbit and operated it throughout the life cycle of the mission? And so all that data needs to be available to them. And so it has to be archived in a way that's easily accessible and that the tools are there so they could actually process that data and make some sense out of it and do analysis from it. So another part of Phase F is making sure that any lessons learned during this operational phase have been archived and again, in a way that people can get to it because other mission designers and other scientists who are thinking of doing similar type projects to what you've done may want to look at those lessons learned to see, well, what went well and what didn't go so well, and what would you recommend for the future if someone was to build a similar system. One of the other big things that you have to do in Phase F is make sure that as you close out the system, that you've properly disposed of both the on-the-ground equipment, right, all the computers and everything else that's being used to work the satellite during its operational phase, but that the actual satellite itself is disposed of properly. And so the decommissioning and the disposal of the satellite is a key part of Phase F. As Phase E is wrapping to an end and the spacecraft is dying, you have to make sure it's healthy enough at the end of the mission to guide it back into the atmosphere if there's any chance that it may not self-destruct. Many spacecraft are built very lightweight. They'll burn up in the atmosphere, but a lot of times there's titanium and other materials on board that may survive. And so in the case of trim, we have to leave some fuel on board to be able to re-enter the atmosphere in some amount of control to target the ocean so that it's safely away from people, knowing that some larger components of the spacecraft may come down intact. And so the end of Phase E planning leads into the next chart, which is Phase F. And so Phase F is where you widen the mission down. It's completed its objectives. You're going to either dispose of the mission into the ocean. If it's going to have to stay on orbit, you want to passivate it as much as possible to make sure that it doesn't have the ability to explode in orbit, which could cause debris that could harm other satellites. And that can happen when you leave a satellite alone and maybe batteries are not tended to over time. You also want to make sure that it doesn't radiate RF energy because as it's living out its life and communicating with the Earth, that's great, but then when you're done with it, you don't want it to interfere with the communications to other satellites, and so you need to go through a passivization exercise that gets you to Phase F, where the mission is complete and you're able to move on to a new mission. So I use the space shuttle as an example. In the last year or so, the space shuttle ended its 30-year career and went into Phase F, where you now had to worry about things like which museum was going to get a space shuttle and how do you archive all the data, how do you get all the lessons learned. A critical part of Phase F is what are all the lessons we learned throughout the system, development operations. Let's make sure that other people can learn from that. And so let's make sure they're documented, make sure that they're transferred to others. You have meetings on lessons learned to try to make sure that the next designers learn from the success of that vehicle or the failure of that vehicle, whatever it might be. So the other thing that was learned during the shuttle lessons learned exercise, I sat in on some of the discussions over time, was that there's a couple key things about the shuttle, and so I'll just mention those as I close out here on Phase F, is that the shuttle, they did a great job in many of the design elements and it operated wonderfully. There were key areas, though, that didn't work out quite as planned. Early on, they thought the shuttle would be reusable in a way that was like an airplane. You would pull it into a hangar, fix it up, and send it back out on the runway. It would take off again. And in that scenario, you could fly the shuttle maybe 200 times a year, 100 to 200 times a year. And if you could do that, that's a lot of flights a year, many times a week. Just like airplanes, you could bring the cost of carrying cargo to space down to a very low level. Was that practical? Was the technology really mature enough to make those assumptions in the 1970s? It didn't quite play out that way. It became much more complicated. Every time you fly a human spaceflight vehicle, it takes a lot of care and feeding to make sure that all the systems are operating well and that it's going to be safe for the next crew. And so it turned out to be much more expensive to process the shuttle and get it back to a launch pad, and it took a lot longer than what you would see maybe in an aircraft operation. So again, designers do the best they can, but sometimes assumptions are made that don't always play it operationally. The other thing that was learned in the shuttle program is the main engines of the shuttle during the development were tested and tested and tested. They were tested under flawed conditions. They were tested under nominal conditions. A lot of engines were blown up down at Marshall Space Flight Center and at Stennis. So a lot of destructive analysis of what happens when a turbine blade cracks, what happens when it's overheated, what happens when it spins too fast. They did that all during phase A and phase B with the thought that all of that data would come in handy in flight and that they would keep improving the design before the development cycle was done to get the optimal engine. And as you see, we never had a problem with shuttle main engines that caused an abort of a mission. Those engines really held up well over 30 years of operations. And so a lot of good lessons learned from every mission that we fly. And I think it's a critical part of Phase F that people forget sometimes, is that those lessons learned need to be plowed back into operations, so in development.
During the closeout phase, the independent technical review team is going to come back in one last time to assess whether, in this case, the project is ready for decommissioning the assets both on the ground and in space. And so let's talk a little bit about what they'll be reviewing at the decommissioning review. So they're going to come in and they're going to look for that first, are the reasons for the decommissioning properly documented? Maybe there was a spacecraft failure. Maybe the science mission has been completed. All the science has been collected you need from that spacecraft. But you want to know that you've clearly documented why you're going into this final decommissioning phase. They're also going to look at that all your plans are completed and that all the plans for disposing of both ground assets and space assets are compliant with any government safety regulations, environmental rules, and anything like that. Because you might have toxic substances, you might have other things you have to make sure you take care of in a safe way. They also got to make sure that your operational plans for contingency situations are documented, because everything we do at NASA when it comes to operating spacecraft and even designing and developing them on the ground, we always think about contingencies, and we want to make sure that the team is prepared not only for nominal disposal, but just in case something was to go wrong, what are the reactions that we'd want to do? It's always better to think those through ahead of time and document them than to have to think them up on the fly at the time. So they'll be looking to make sure your contingency plans are all in place, and that the operations team, the people who will be executing the disposal and decommissioning, know both, they've been trained both for the nominal and the contingency situations that might arise, so that training's all been completed. They're going to want to see proof of that, and that any risks that are associated with the disposal have been identified, and that there are mitigation strategies in place to deal with any risks that you've identified. Plans for disposition of any system's assets are complete. When you wrap up a mission at NASA, typically you have a lot of computer equipment and other things that you have to dispose of. Sometimes those are given to other projects. Sometimes they're older and not valuable to anybody else and they're just disposed of. But you have to have a plan for how you're going to handle all of that. And most importantly, not only equipment, but you have a lot of data that you've collected throughout the mission, both engineering data that tells you about the health of the spacecraft throughout the mission life that you might want to archive off, as well as all that important science data that you might have collected. So they're going to want to know that you've got plans for archiving all of the data that's been collected and that you've got the tools in place so that anybody else who wanted to look at that data downstream would have the ability to go in and be able to look at the data and have the tools to do it, and that you've got the resources, because you're going to have to spend money to close all this stuff out, archive everything. They're going to make sure you got all the resources in place to do that. And lastly, and always most importantly at NASA, we want to make sure that all the lessons learned have been archived and that they are in a form that's available to the broader community, so that other missions in development or in operations can learn from everything that's been learned along the way from the beginning of this mission all the way to here when you've finally reached the closeout. There are no additional resources for this subunit. Feel free to skip ahead to the next video.